Hello and welcome to the series of videos in queuing theory. I'm going to start by introducing some common terminology in queuing theory. Now first, let's take a look at some examples of queuing systems. For example, in a bank, if a customer goes to the bank, he or she will wait in the queue until he or she can be served by the bank teller. Once all the transaction of this customer is complete, she can leave the bank. Another example is a pizza restaurant. It takes the orders from the customer, so customer sends the order to this restaurant, and then if there's a queue, then the restaurant will do it one by one until finally the pizza for a particular customer is finished and it will be sent to the customer. Another example here is a naval shipyard. For example, it has the job to repair the ship. So whenever a ship is broken, it will go to this naval shipyard. If there's a queue, it will wait in the queue. And when it comes to its turn, it will be repaired. And then once it is complete, it will return to the state of a good ship again. Learning queuing theory is useful for us to answer the practical questions related to a queuing system. For example, we would like to know what is the expected number of customers present in the queue. Maybe we would also like to know what is the expected time that a customer typically spends in the queue. And suppose we're a bank manager and then we would like to ensure that only 1% of all customers will have to wait for 5 minutes or later. And then we'd like to know how many tellers should be employed. Okay, so queuing theory will help us to answer such questions. When we talk about a system like a queuing system, it has the input and the outputs. So let's start by talking about the inputs for a queuing system. The input to a queuing system is the arrival process. Customers arrive, and we also call the customers as arrivals. There's an assumption about these arrivals. The assumption is that there's no more than one arrival or one customer can occur at a given instant. So at a particular time, at most, only one customer can appear in this queuing system. In another term, it is said that we do not allow bulk arrival. Another common assumption in the queuing theory is that the arrival process is unaffected by the number of customers present in the system. So it means that when the system, for example, a bank, whether it is crowded or it is empty, it will not affect the arrival process. The customers who want to come to the bank will still come to the bank, enter the bank, regardless of the bank is crowded or empty. Okay, so that's what the assumption says. Of course, you may think that that assumption may not be realistic all the time, and then yes, you're correct. At least there are two exceptions. The first exception is when the arrivals are drawn from a small population. Let's say we have a naval shipyard and our population, which means the ships that we have, we only have 3 ships. And these 3 ships, currently they are all broken. They are here in our naval shipyard. So of course, we will not expect any other arrival coming to our naval shipyard, right? Because we only have 3 ships. All 3 ships are broken. They're already here. So there will not be any more arrival to our naval shipyard. And we will learn about this in the model that is called finite source model. The second exception is when the arrival rate decreases when the facility or the system becomes too crowded. The example for this is when you are in a hurry to have lunch or something, and then you go to, let's say, a restaurant, and then you find the restaurant is super crowded. You may want to leave and not decided not to enter that restaurant. Now let's talk about the output of a queuing system. So if the input to a queuing system is the arrival process, customer arrives in the queuing system, the output of a queuing system is the service process. Because once a customer has been served by the server, he or she will leave the system. And then the service time, the time it takes to serve a customer, is governed by a service time distribution. We will talk about this distribution later. Okay. And there's assumption here for the service process, which is the distribution of the service time is independent of the number of customers present in the system. So this means that, for example, the example of the bank teller again, the bank teller will serve a customer with the same service time distribution. For example, if the average to serve a customer is 3 minutes, then it will stay the same with the average 3 minutes, regardless of just one customer present in the systems, or there are so many customers present in the system. Okay, so it doesn't matter how many customers in the system, it is assumed that the distribution of the service times remain the same. So the bank teller will not work faster, will not work slower um, when it comes to the whether the bank is crowded or the bank is empty. Now let's talk about how the servers are arranged in the queuing system and also about the queuing discipline. Here we see two types of server arrangements. On the left, the parallel arrangement. Here we have, for example, two tellers. They have exactly the same function. So customers may create a queuing line, and then the first customer in the front of the line, she may go to the left teller, she may go to the right teller, whichever teller is empty, because the functions of both tellers are the same. And once she's finished with her transaction, she may immediately, I mean, the customer may immediately leave the system. In the series arrangement, we have two servers arranged in series. For example, the first station or the first server takes the order, and then the second station or the second server handles the payment. So when a customer enters this queuing system, she must go first to the first server, makes her order, and then once she finished with this order station, she must go to the second station before she leaves this system. Okay, so these two server order and payment, they have different function. And that's why it is called a series arrangement, because a customer has to go to the first station and then she needs to go to the second before she leaves the system. Okay, so in parallel, all the server have the same function, so a customer can go to whichever he or she likes. But in a series arrangement, each server has its own function, and then the customer has first to go here, and then next go there, and then next go there until finish, and then she may leave the system. Now, about how the queue is formed in the system, we have several queue disciplines. For example, this is the most common, first come, first serve. So whoever comes first will be served first as well. So example, you're queuing in a bank. Usually the first person in the front of the line will be called and will be served. And this is not very common, last come first serve. For example, in an elevator, in a super crowded elevator, the last ones who squeeze into the elevator will become the first to be served by the elevator, because the door will be closed and then the elevator will move. And then maybe the queue discipline is also the service happens in random order. So from all people in the queue waiting to be served, the server will pick one randomly. For example, here is when you call a customer service or something and there are several people online, the customer service may probably randomly pick any of the customers waiting in line. So to summarize, the input to a queuing system is the arrival process. Customers arrive in our system, coming into the system. And then the output of a queuing system is the service process, because customers go out from our system once they have been served. The servers in the systems may be arranged in parallel, or in series. And then the queue discipline in our system usually is first come, first serve. So that's all in this video. And in the next one, I'm going to talk about how we may model this arrival process. We're going to model how customers coming into our system. So thank you and see you in the next one.